Hi, everyone. Thanks for joining us for our presentation. Today, our discussion will be about the additive manufacturing techniques for regenerative rocket nozzles. For our presentation, we are going to look at the background information about rocket nozzles and how problems can arise using traditional techniques. And then we're going to look at two advanced processes that deals with these problems, and then recommendations that our team chose and how future work can be implemented on these rocket nozzles. Aeronautic systems, such as the liquid rocket engine, are becoming increasingly complex and tightly coupled. There are high demands and intense competition to develop stronger, lighter, and more durable components while minimizing production costs, manufacturing processes, and material waste. A critical component is the regenerative cooled nozzles, which allows the optimal expansion of hot gas and increased temperature of the propellant for performance due to the coolant channels lowering the inner wall temperatures. There are four conventional techniques of fabricating channel wall nozzles. The first one is the fabrication of internal hot gas wall liner. The second is machining the coolant into the liner. The third is the closeout of coolant channel integral to the liner. And the last step is the fabrication and bonding of the manifolds. The difficulty lies in the close-up step, where the jacket is joined to the inner liner at the wall of the channels. This is particularly important because the quality is in strict requirements associated with the coolant fluid pressures, thermal shock, and mechanical load faced by the channel walls and the liners.
Here is a picture of the channel wall nozzle with parts including the coolant channels, the inner liner, and the closeout parts. The traditional fabrication method that we're going to use for comparison is the laser welded sandwich wall closeout technique. This technique uses laser beam in what we call blind welding. Now, the laser beam follows one X-ray tracker while penetrating through the outer jacket, creating the joint, while another X-ray inspects the joint. Now, this process is repeated for all wall channels on the inner liner. Although laser welding of the closeout parts is a more recent approach for fabricating the channel wall nozzle, it has its challenges that can be seen here. Now, the high cooling rates as a result of high speed leads to cracking and also formation of brittle, non-ductile, and non-homogeneous microstructures. Now, this process, as I said before, is repetitive and it requires continuous inspection, which makes the process longer. Also, the blind welding aspect makes it difficult to inspect the joint visually. And there's also safety issues related to laser that contributes to high implementation and maintenance cost. To solve these challenges, the team considered two advanced manufacturing processes, one being the laser wire direct closeout and the second one being the blown powder direct energy depositions. And the team compares the two and the traditional manufacturing method using the following objectives. One is reduce the cycle time and the number of steps during fabrication, reduce the number for specialized tooling, improve inspectability by reducing offline inspections and making default parts more apparent, improve microstructure properties at all bonding regions, and improve nozzle performance and average life.
The first manufacturing technology we'll be discussing is laser wire direct closeout, abbreviated as LWDC. This method integrates a subcategory of direct energy deposition known as laser metal deposition by wire. As you can see on the figure, a metal wire is fed by a nozzle to a laser focal point where it is essentially melted or welded onto the substrate or the previous layer. This method is specific to the closeout stage, so the inner liner and the channels must be prefabricated. So to create the closeout jacket, the inner liner is placed on a rotatable robotic arm, which allows for a bigger build base. Metal deposition starts at the stock or the bottom of the nozzles, so future layers can be built on top of it. Essentially, the laser beam is melting the wire to the previous layer and channel walls to create metallic bonds or welds. Various parameters are monitored to maintain the bead geometry and the bond at the interfaces. Note, however, that the metal deposition does not droop into the coolant channels. One of the things this method allows us to do is create bimetallic parts. As you can see in this portion of a nozzle, the inner liner and the closeout jacket are made out of different materials. Usually the inner liner is fabricated with a metal or alloy that exhibits good thermal conductivity. Sometimes there are intermediate layers of different materials to enhance the bonding between the two dissimilar metals. Configuration of the materials should also be considered to balance the additional weight and the increased thermal performance. The axial configuration is optimal for lowering wall temperatures near the throat of the nozzle, which is a high temperature flux region, while the radial configuration attempts to reduce the wall temperature throughout the nozzle. In terms of the material characteristics, laser metal deposition by wire has similar properties to that of blown powder deposition, but usually has less porosity issues. As you can see on the figure, there are still some issues with porosity remaining in the bimetallic part. In terms of specific mechanical properties, it really depends on the material. With laser metal deposition by wire of steel alloys, there is an increase in brittle sigma phases as the number of layer increases, which degrades the strength of the build, as indicated by the lower ultimate tensile strength of nickel-based alloys for laser metal deposition by wire. Laser welding generally outperforms laser metal deposition in terms of mechanical properties.
The second manufacturing technology we'll be discussing about is the blown powder deposition process. This process also falls under the directed energy deposition category. As you can see in the figure, the blown powder deposition process accelerates powder through a nozzle into a melt pool. The melt pool is created by a ladder energy source, causing a weld bead to be deposited. Here, the powder is made of the metal or superalloy we want to use in the fabrication process. This powder is blown into the melt pool using an inert carrier gas to reduce oxidation in the high temperature deposition. This system is attached to a robot that controls a toolpath defined by the CAD model. The blown powder system and robot allows for complex freeform structures to be built. Various optics can be used to vary the spot size, which in return controls the size of features that can be built. The blown powder deposition process is attractive in that it can be used to form integral channels within components in one build, which significantly reduces part count and eliminates many of the process steps in the nozzle fabrication process. Additionally, it is capable of fabricating large-scale parts since it's not restricted to a build box like powder bed fusion. NASA conducted tests on subscale nozzles fabricated using blown powder deposition technology to further understand and implement the technology for full-scale channel wall nozzle fabrication. The test used subscale nozzles made of Inconel 625, which is seen on the top image, and JBK75, which is seen on the bottom image. Both JBK75 and Inconel 625 are high-strength superalloys suitable for such applications. The JBK75 nozzle completed hot fire tests that totaled to 4,170 seconds in liquid oxygen and hydrogen environment, while the Inconel 625 completed hot fire tests that totaled to 1,072 seconds in liquid oxygen and kerosene environment. The test results, which are summarized in the table, and the inspection of the nozzle after the fire test, which can be seen on the image, showed that both the JBK75 nozzle and the Inconel 625 nozzle were in good condition and leak-free. This successful test shows that blown powder deposition is a feasible technology for the fabrication of channel wall nozzle structures.
Although the two methods met the objectives, blown powder direct energy deposition technique was more superior because it formed the entire channel wall in one single build, and this reduces cycle time and eliminates manufacturing steps.
The target of the future work should focus on increasing the scale of the nozzles, reduce costs, and improve performance. Some areas of future work to attain the targets include exploring the integration of multi-access machining systems to create a hybrid, additive, and subtractive manufacturing method that reduces surface roughness. The second is using different materials to fabricate the channel wall nozzles in an attempt to improve performance and/or cost. And in conclusion, both techniques reduce the number of fabrication steps and improve microstructure properties, thus reducing cost and time, as well as improving the performance of the rocket nozzle.